Our next paper is entitled Acquiring the Reflectance Field of a Human Face by Paul Debevec, Tim Hawkins, Chris Chu, H.P. Diker, Wesley Sorokin, and Mark Saga. It will be presented by Paul Debevec.
Thank you, Leif. The work that we've been looking at over the last few years has mostly concerned ourselves with capturing light in the real world and then using light that's been captured in the real world in computer graphics. What we've typically been doing is going out and somehow taking an omnidirectional high dynamic range image of a particular environment and then illuminating a set of synthetic objects with these environments. And the work that I'm going to talk about today, we wanted to extend these techniques to be able to capture light in the real world and then illuminate not synthetic CG objects, but to actually illuminate objects in the real world, in particular human faces. For an overview of this talk, I'm first going to review some related work. Then I'm going to discuss our technique for relighting faces with sampled illumination without changing the viewpoint. Then I'll talk about some techniques where we can synthetically change the viewpoint on the face. And then I'll finish up by discussing some ongoing work and the conclusion. There's a number of pieces of work in the last few years at SIGGRAPH that have really done a great deal to pave the way toward acquiring and rendering realistic models of human faces. I'd just like to highlight two of them right here. One of them is Hanrahan and Kruger in SIGGRAPH 93, where they did simulations of light hitting the layered surfaces of the skin, taking multiple scattering bounces and then generating renderings that way, which is a new way of simulating the reflection of skin, which is more physically accurate. Also, most recently, Marshner et al. At Cornell did some of the first reflectometry of measurements of human skin, and they had a real live subject. They took pictures from different angles and illuminated the subject from different positions, and from that we're able to come up with a BRDF of skin reflectance. Basically a general single BRDF for the average of the subject's forehead. And that's the first work of its kind. I'm now going to talk about our techniques for capturing realistic facial models and then relighting them with sampled lighting environments. And I'll start by talking about our basic approach. What we're going to do in this work is to try to, as much as possible, directly record how the face as a whole interacts with light. And that's to say that we are going to try to directly record how the face transforms incident illumination falling on the face into radiant illumination that you can see. And we'll call this is acquiring the 8-dimensional reflectance field of the human face. And you can see that a reflectance field is basically, we're denoting by R, and you have a field of illumination coming in, a field of illumination going out. Each one of these things is a 4-dimensional quantity of the light going into the face and coming out. And what we're going to talk about here are ways of acquiring slices of this reflectance field and then using them to generate new renderings of the face from different angles and in different lighting conditions. So the principal apparatus that we have developed for this work is something we call the light stage. And this is a picture of it. Essentially what it is a device that can spin a light around a person's head in a relatively short amount of time and illuminate them from every possible angle. The way that this first version of the light stage works is that there are 2 bars. The light is attached to the inner bar. This whole double bar mechanism rotates around in theta here to get different azimuthal angles. And then the second bar here, which we call the phi bar, slowly comes down a little bit each rotation to get the light to come down at different latitudes. And this first device is completely hand cranked by a couple of cords, but we have some ways of getting it to be relatively well registered. The light goes from the top to the bottom and gets all the directions in about the span of a minute. And to check whether we were getting the directions correctly, we took a long exposure photograph of the light starting at the top and going to the bottom, which looks like this. So this is a 60-second exposure of the light stage in operation. Now, while we wait for the light to go from the top to the bottom, the image of the face is recorded by 1 or more video cameras, and recording at 30 frames per second in a 60-second in a 1-minute twirl of the light stage, that gives you 2,000 different lighting directions. which look like this. We actually get a 64 by 32 grid of the face lit from every possible direction in theta and every possible direction in phi. And what I'd like to do now is show a clip of video, which is a clip from from a piece in the electronic theater, that shows how we can take a data set like this and use these images and transform them to appear, to generate faces, to generate images of the face as if it would be lit in any possible lighting environment. Thank you. So these are a couple of stills of the face illuminated with a couple of different lighting environments here. This is a synthetic environment, and these are some light probe images. And all of these are available as data sets if you're interested in the light probe image gallery, which you can find at debevic.org. So one of the goals of our project was also to be able to perform this illumination task as efficiently as possible, so that we could hopefully be able to do this in real time and do it interactively. So let's take a look at our data set a little bit more closely and look for some ways that we can do this more efficiently. Let's for a moment consider a particular pixel of the face. Let's say this pixel right here on the forehead. We actually have 2,000 images of that pixel with the light coming from every possible direction, 64 directions around in theta and 32 directions up and down in phi. What we can do is form an image out of those 2,000 directions of illumination, out of those 64 by 32 data sets, that looks something like this. So this is the color of the pixel as the light moves around from left to right and up to down. You can see that when the light is behind the head, the pixel is quite dark, but when the light moves in front of the head, you can see some of the flesh color. And when the light moves at the mirror angle to the surface normal, that's when you get the specular reflection, which you can see as this white spot over here. There's another effect that we get in these reflectance functions, which is that we tend to, when the phi bar goes in front of the camera, it actually leaves a black streak along here, which we algorithmically remove. And also, when the light is directly behind the head, you tend to get a lens flare from the light shining into the camera. If we look at a more interesting area of the face, or a less convex area, like this pixel right next to the nose, you can see that for some of the lighting directions, it actually is going to cast a shadow on that pixel, because the nose will block the light from hitting that area. And that is actually seen right here. That's the shadow of the nose in this reflectance function. Another reflectance function, which I think is particularly interesting to look at, is inside the ear. And there's this concavity right here that we're looking at. And so you only get a particularly bright response when the light is visible at the bottom of this concavity, which is a relatively small area. But when the light is behind the ear, you actually still get a return of some sort, which for some reason we can't see today, but we'll fix that in the future, which is sort of a deep red, and that's because the light is hitting the back of the ear, scattering through the ear, and then illuminating the front. So one of the nice things about these reflectance functions is that they implicitly include all of the effects of self-shadowing, of subsurface scattering, and mutual illumination that the face exhibits. And so you can actually perform this relighting directly on these reflectance functions rather than by summing a whole bunch of images of the face together. And that is just done as follows. If you have your map of incident illumination, which you've resampled to be in your same 64 by 32 directions of incident light, you can simply multiply that by the reflectance function, component-wise, because the reflectance function says how much that pixel responds to light coming in this direction. That's how much light is coming in this direction. And then you get a lighting product. If you just sum up all of the pixels in this lighting product image, then you can get a value for your final rendered pixel. Now, just reorganizing the computation like this doesn't actually save us anything, except for the fact that you can notice that these reflectance functions are usually relatively boring functions. There's not a terrible amount of exciting stuff going on in them, which means that if you put them into frequency space, for example, by projecting them onto the discrete cosine basis, that you will end up with a representation of this reflectance function that can be perhaps only 10% of the coefficients as you had before. So you can rewrite your equation in terms of a DCT basis by running the DCT on the light map, running the DCT on the reflectance function, which sets about 90% of the coefficients to 0, compute your lighting product and then your rendered pixel, and that saves you about maybe a factor of 8 in computation and perhaps a factor of 8 in storage as well. So as a result, you can relight faces in real time, and that allowed us to write an interactive demo, which is available for you to play with if you're interested at the Creative Applications Laboratory here at SIGGRAPH, that allows you to synthetically to bring up any one of several facial models, illuminate the face by any one of several environments, spin the environment around the face if you so wish, or put any number of light sources of the amount of intensity or harshness or diffusion or color that you would like, and it all runs in real time. So this so far has shown us, so far we've discussed how to render the face under the same viewpoint as the original camera position. What we would like to be able to do is to change the viewpoint. Now, one way to change the viewpoint would be to just capture all of the viewpoints to begin with. We know that by using the light field technique, we could, for example, have a two-dimensional array of cameras all around the face, and then just using the light field, interpolate any kind of view that you would want. That would mean that we would be acquiring a complete reflectance field of the face. In this work, we had two cameras, and so we looked at some ways that we could interpolate or extrapolate a view from one particular position to novel viewpoints. And this required looking at the way that skin reflects light, because skin is not a Lambertian surface. That means that as you change the viewpoint, its appearance is going to change. In particular, its specularities are going to shift in position. So we wanted to be able to study exactly how that happens so that we can predict this effect accurately. This is an image that shows the two ways that light can interact with skin. One way is that the light comes from the world, then just bounces specularly off of the oil layer on the front of the skin, and then returns, in which case the light is going to stay the same color. It'll also maintain its polarization. The other thing that can happen is that when light hits the skin, it can actually enter the epidermal and dermal layers, which means that it will pick up the color of the skin and then come out at some relatively randomized direction, which means that it's going to be a more diffuse reflectance. It will also tend to depolarize the light if it came in with any particular polarization. So what we're going to do is try to look at the specular and the subsurface components of the light individually, because that way we can model each one of them in a relatively simple manner, and that will allow us to extrapolate the skin reflectance from one direction to another direction. So we did a reflectometry experiment that is described in the paper, where we used a set of polarizers to separate the specular components, the specular and subsurface components. This is a normal image of a face, and what we also did was take the same image, polarizing the light source vertically, and then placing a horizontal polarizer on the camera. And what that does is it will block all of the specularly reflected light, producing an image like this that is just of the subsurface component of the reflection. Now you can subtract this image from the first image and then look at the specular component on its own. So this allowed us to perform a reflectometry experiment where we looked at several angles of incident light and radiant light to examine what the subsurface and the specular components were doing. And we noted a couple of things. First of all, the subsurface reflection exhibits a chromaticity falloff. That is, when you get to grazing angles, the amount of saturation of color in the subsurface component tends to diminish. Otherwise, it's generally a pretty Lambertian type of reflection. The other thing we found in the specular component is that it actually seems to be monochromatic, the color of the light source as we would expect, and it obeys basically the Torrance-Sparrow microfacet distribution behavior. So using this process, we're able to come up with basic models of how the subsurface and specular components would act. Now, in our light stage, we didn't want to have to run the thing twice with different polarizers. So instead, what we did is we separate the reflection components based on color. And since we know how the chromaticity behaves with angle, we can actually do this color space separation effectively. So if we have our original reflectance function, this is going to be the way that the skin reflects light toward a given camera. What we need to do to generate a rendering from a new viewpoint is to resynthesize this reflectance function to be the way it would look if that piece of skin were observed from a new position. So what we'll do first is split the reflectance function into its two components, which we do based on color space analysis, into its A subsurface component and B into its specular component. Now, by analyzing the subsurface component, we can figure out a variety of things about this particular piece of skin. In particular, one of them is its surface normal. And once we have its surface normal, then we can actually figure out where the specular component was pointing originally and where it should be pointing in the new rendering. So what we do is look at the specular component closely, and as it turns out, this actually gives us a direct readout of the microfacet distribution of that particular area of skin. And then using a technique described in the paper, we can resynthesize a new specular component based on these pixel values that is appropriate for the new viewpoint, where the specularity will be shifted. Then finally, we add the subsurface component, which we modulate based on chromaticity falloff, with the shifted specular component to form a final reflectance function. And you can see that the specular reflection has been shifted somewhat. In this particular case, we actually had a second camera at that point of view that we have resynthesized that to, that allowed us to compare how well our extrapolation method would predict the way that the skin actually reflects light in that direction, and there's a comparison. So in this case, at least, there seems to be good accuracy. We also did a basic experiment of taking an original picture of the face from a particular viewpoint, and then rendering a synthetic view of the face from a completely novel viewpoint to see if these things would at least qualitatively match up. So this is the original image, this is a novel rendering from a new viewpoint, and you can see it still looks hopefully like specularities are in the right places and are in about the right intensities, and we have the specular roughness correct. Now, something we can also do if we want to use this kind of data in a more traditional renderer, where we need to have a BRDF at every particular point of the skin, is that we can distill from our reflectance functions things such as the diffuse color, the specular color, and the specular roughness. And we describe that in the paper. These are a couple of maps that we covered for this particular subject. We get a map of the surface normals, the diffuse albedo, the specular intensity, and the specular roughness. And all of these vary spatially across the face. So what I'd like to do now is show a video that describes a little bit more thoroughly our technique for rendering the face from novel viewpoints.
Using the light field technique, a two-dimensional array of cameras would allow this to be done directly from captured data. In this work, we capture data from only two cameras and use a range scan of the face and a reflectance analysis technique to synthesize the face from novel viewpoints. The reflectance analysis is performed on a transposed version of the captured data set. If we consider a single pixel of the face across all of the captured lighting directions, we can construct a new image we call a reflectance function. Here we see a mosaic of these reflectance functions containing 1/32 of the total data set. Each reflectance function encodes how the face scatters each direction of incident illumination toward a particular viewpoint, and includes all the effects of shadowing, mutual illumination, and subsurface scattering. To transform the reflectance function to a novel viewpoint, we first separate the function into its specular and subsurface components using a color space technique. We then modulate the subsurface component based on its observed chromaticity falloff, and warp and scale the specular component using a generalized Torrance-Sparrow model. Adding these transformed components together yields the reflectance function resynthesized for the novel viewpoint. To render the illuminated reflectance functions at the correct positions from novel viewpoints, we recover a geometric model of the face using structured lighting. The normals of the model are noisy, so we instead use surface normals computed from the reflectance data. We then render views that are geometrically from the original camera viewpoints, but with the pixels shaded according to the novel viewpoint. Lastly, we project these renderings onto the geometry, thus placing the correctly shaded pixels in the correct positions and producing the final render. For each of the lighting environment examples, we first show the complete rendering and then show the resynthesized specular component alone. In these examples, the illumination environment remains fixed while the face nods from left to right. Thank you.
So the last experiment that we did with our technique was to try to see how well this can predict the way that light behaves in the real world. So we did this following experiment. We took our subject, this is actress Jessica Vallow, took her and placed her on the Berkeley campus and took a real picture of her in this real environment. We then took a lighting measurement of what the illumination was like at this particular point that she was sitting, and then generated and then used this lighting to illuminate the synthetic model of her face, which we then matched to be from the same viewpoint as in the photograph. And then we took this rendering of her face, composited it on top of her face in the original photograph, and were able to generate at least a qualitatively similar result, which was the goal of our work. So a couple of things that we're looking at doing in the future are, of course, to animate these faces. We're also looking into capturing more spectral samples instead of just R, G, and B, and hopefully get better color matching. And then lastly, to use high-speed cameras so that we can work toward achieving real-time capture, so that we could actually capture the reflectance properties of actor as they read lines for a scene, for example. So in conclusion, we have presented, first of all, a light stage apparatus which is able to capture slices of the reflectance field of a human face. We've shown a technique for correctly relighting faces, generating renderings of faces in new environments without doing traditional ray tracing or radiosity, but just by directly using images as much as possible. And then lastly, a technique for extrapolating images, renderings to novel viewpoints. I'd like to just conclude by thanking a lot of the people who helped make this work possible. Thank you. Got 2417 on that.
Not bad, not bad. That was way better than yesterday.
Oh, yeah.
Yeah?
That was incredible.